Okay, guys, so today I'm going to go ahead and introduce you to double integrals in polar coordinates. So first of all, I need to discuss what are polar coordinates. So maybe you've already seen this before, maybe not. We will go ahead and take a look at them. So what happens is like when you have normal x and y coordinates, right, that you're so used to, this is called Cartesian plane. So basically you have some x, and x is the distance right or left from the origin, and y would be the distance up and down, right? But now what happens is we want to switch to a different coordinate system. So a point, for example, with coordinates, let's say 3, 2, will have different coordinates in polar coordinates. What is it going to be the coordinates? So it will be also two numbers, and we need to figure out what they are. So by definition, the first number is going to be the distance from the point to the origin. So basically, what would be the diagonal of this triangle? And so the diagonal by Pythagorean theorem would be just square of one side plus square of the other side, and then we take the square root. So this would be square root of 3 squared plus 2 squared. So this is called r. So r is the distance from the point to the origin. And then you also will have theta. And theta would be the angle that this line segment makes with the positive x-axis. So in other words, this angle right here, that's going to be theta. And how would you find it? Well, in a triangle, what you can do is if you know that tangent of an angle is equal to opposite side over adjacent side. So opposite side would be 2 and adjacent side would be 3. So tangent of that angle would be 2 divided by 3. Now you can solve for theta by applying the inverse tangent. Now it becomes a little bit more complicated when you start dealing with what happens in the second quadrant, third, fourth quadrant. So that's kind of like there are a lot of details here that you guys are not going to need. But generally, the idea is this, that taking a set of coordinates x and y, we switch them to new set of coordinates r and theta. So each point can have coordinates in one system and can have coordinates in another system. So next, what I want to discuss is what would be the equation of a circle in polar coordinates. So let's start with an example. So what happens if it's circle, which is going to be why we need it really. Any circular regions, it's going to be a lot easier to integrate in polar coordinates as opposed to the Cartesian, right? The x and y stuff. Okay, so circle in polar coordinates. What's going to be an equation of a circle? So let me show you what happens. So first of all, before we do that, I need to write down equations that connect the Cartesian coordinates x and y and the polar coordinates. So generally speaking, x would be this side right here, right? So that's the adjacent side. So we know that cosine of theta is adjacent side over hypotenuse. So that would be like x divided by r. That's cosine of theta. Sine of theta would be opposite side over hypotenuse. So that's going to be y divided by r. So this is going to be important for us because that will give us a connection between x and y and r and theta. So solving the first equation for x, we would get from here x equals r cosine theta. And then solving this equation, we'll get y equals r sine theta. So this connection you actually have to know. So this is something that you will have to know and memorize, okay? And it's not that hard to understand it. I think just from the definitions, from looking at the triangle and just from the definitions of cosine and sine, you get the connection. So generally speaking, if you have a circle, so center of the circle, we're gonna assume it's at the origin. So center is at the origin. So that would be 0, 0. We've got equation of a circle, and you should already be familiar with that. It looks something like this. X squared plus y squared equals a squared. A would be the radius of the circle, right? Now, I want to go ahead and convert this equation to polar coordinates. So how do I do that? Well, instead of x, I am going to plug r cosine theta right here. And then instead of y, I'm going to plug r sine theta. So that's going to go in here. All right, so what will happen? So let's go ahead and plug it in. So we get r cosine theta. Then we need to square the whole thing. So we are plugging that whole thing, and so we square that plus Instead of y squared, we get r sine theta, and we square that. And that's equal to a squared. All right, now, when we square a product, we can just square each term in the product, right? So it's going to be r squared cosine squared plus r squared sine squared, right? And that's equal to a squared. Now, notice that we can pull out r squared, and then we'll get cosine squared theta plus sine squared theta, and then that's equal to a squared. But you may already recognize that this right here, this expression right here, that's actually equal to 1, right? So remember, there was this one trigonometric identity that was telling you like the most important one, because sine and cosine are really coordinates on a unit circle, and on the unit circle, x squared plus y squared is equal just 1, because it's a unit circle, so radius of it is 1. So that's where that comes from. But anyway, now you can see that r squared is just a squared. Now, if we assume that a is a radius, it's a positive number, so let's just assume that r is also positive. So here we got an equation, r equals a. So that's an equation of a circle, okay, with radius a in polar coordinates. So it makes it a lot easier, right, with just r equals some number. So with that said, how do we set up limits of some common regions when we do integration? And we're going to look at integration in the next video. But I want to just talk about the setting up of limits. So if you have a circle and you want to integrate over the interior of that circle. So for example, you have a circle of radius 3, right? So something like this. And your integration is going to be over that whole circle. So integration over this whole thing. So how are we going to do that? Okay, so what you want to do is switch to polar coordinates. So generally what you want to do is integrate some function over that region, we'll call it d, and then dA. dA is going to be like dy dx or dx dy, depending on the type of preference. So this is your region D, right? So this right here, that's D. So if you were to use regular coordinates, it's going to be actually kind of difficult to integrate it. So imagine that you have a circle x squared plus y squared equals 9, for example. So that's radius of 3. So you had to integrate it. You would have to integrate from -3 to +3. And then your bottom curve is going to be like this one, which is actually, if you solve this for y, this will become 9 minus x squared square root, but then it's plus minus. So the negative part of it is the bottom. So like this part, that part right there, that's negative square root of 9 minus x squared. And then the top part right here, that's a positive square root of 9 minus x squared. So if you used regular coordinates, right, the xy's, then your x will change between -3 and 3, and y will change between negative square root of 9 minus x squared and positive square root of 9 minus x squared. Now, the problem with that is the roots are kind of nasty, so you might not want to do that. But if you switch to polar coordinates, it's going to be very, very easy. So what we do is, instead of this whole with the roots and everything, we can substitute and instead use polar coordinates. Okay, so in polar coordinates, the way we're going to do this is, first of all, we're going to have order dr d theta. Now you can choose a different order. You just have to worry about the limits corresponding to that, right? Because remember that these right here, these are going to be the theta limits, and then the inside integral, those are going to be the r limits. So you have to be careful with that. So if you put d theta first and then dr on the outside, then you have to switch the limits also. So the way I do it, I always do the theta the outside limits and r the inside limits. Okay, so unless we have a reason why we would change it, I just want to keep it that way. Okay, so for here, how does theta change when you are inside this region? So theta is an angle with the x-axis. So for example, if you're somewhere over here or somewhere over here, somewhere over here, or maybe here, theta will go from 0, right? So that this would be 0. And as you keep traveling around the circle, it's going to go from 0 to 2 pi. So theta for the whole circle will just go from 0 to 2 pi, which should make sense. Now, as far as r, that's the distance. So for fixing an angle, so let's say you fixed an angle, so you're now right here, you want to encompass that whole line segment. So on that line segment, let me make it blue, maybe you can see it right here. How does r change? Well, if you are over here at the origin, your r is 0. And then if you are over here at the end of the like on the circle, then your r, which is the distance, will be 3. So then this will just be 0 to 3. Okay, and that makes it so much easier to integrate because now you don't have these roots and whatever. The only thing you have to worry about, that one other thing that is theoretical, that when you switch from one type of coordinates to another set of coordinates, you actually will not just get dr d theta. So there's this extra term that comes out. It's called the Jacobian, which is something we probably will not have time to discuss, but it's a general idea. As when we switch from one set of coordinates to another, we have to incorporate that Jacobian in there. So that Jacobian actually is very easy. It's just an extra r. So whatever you're going to be trying to integrate here, you will just have to add an extra r. Well, I don't mean add by like plus, but it's really multiplied, right? So this r, extra r, you have to remember it. To help you remember, I sometimes tell my students, remember the pirate. Why do I say that? Why remember the pirate? Because the pirate says R. So when you remember that the pirate says R, you're like, oh yeah, there's that extra R. Because if I get it, obviously you're gonna make a mistake. Okay, well, in the next video, I will go over an example of solving a double integral using polar coordinates.